Welcome to the podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to talk about longitudinal waves and how they relate to sound. So specifically, a longitudinal wave is a sound wave, right?
Right.
What else is required for there to be sound?
You have to have a medium.
You got to have a medium. So that would be a mechanical wave.
Correct.
I mean, we keep talking about the medium as being air, but of course, liquid
Right,
would qualify.
Like waves on an ocean.
Sure, solid would
It's
qualify.
like a string
Sure.
vibrating.
So there's a lot of different possibilities when we're talking about mechanical waves. So sound is a longitudinal mechanical wave, and the longitudinal part you should have saw in section 2, where the wave part or the slinky gets all smashed together,
Right.
and then it gets all stretched out, then it kind of comes back together and it gets all smashed, and then it gets all stretched out. And we would call these points the crest, and we would call these stretched out portions
The trough.
the trough. And this is exactly what's going on with your air particles. When the sound energy is released from your voice, the air particles get all smashed together. They run into each other and they vibrate each other. And it's like they're pulling the air in from both sides, which means there's not many in between. And then the density picks up and then they get really tight together.
The way that I always try to show this is a speaker moves in and out.
Yeah, that's a very good point. So when if you take the covering off of a speaker and you play a song loud enough, you'll see it pulsate.
Right.
And that's sending these compressions out. But they're happening so fast, it looks like it's continuous.
Right.
But in fact, these are individual pulses.
It's not like a string where you go right and left.
Correct.
It's actually in and out.
So this is what a longitudinal wave is. Now, this is very difficult to picture. It'd be much easier to picture this.
Right.
And so that's how we're going to draw these standing waves inside of our musical tubes. So you guys had some straws.
Right.
What else did they have? They had
Well, we looked at boom whackers. We looked at the
Yeah.
Blue Man stuff,
Uh-huh.
the tubes.
and they had the test tubes as well. And so we looked at two different types of tubes, and we tried to compare them to strings. And in my class, anyway, we had a really good discussion about this, where if you had a pipe open at both ends, it was just like a string.
Correct.
And in section 3, we determined that you could get half a wavelength
Correct.
in this space. So L could be half a wavelength. It could also be a full, or 3 halves, or 2, or so on. The same could be said about our pipe open at both ends. So if you had just the right length of pipe and just the right diameter and the same length of string and the right thickness, you could produce the same tone. So much so that if you closed your eyes and just listened, you probably wouldn't be able to tell the difference. These are similarities. The only notes, okay, that these pipes or strings will play are standing waves.
Right.
Some of these standing waves, by the way, sound terrible, and they're not really musical notes, just noise. But if you have just the right length, then you have a note. What's the other possibility for a pipe, Mr. Sadler?
Closed.
Yeah, it can be closed at one end.
And remember, the open had half of a wave, and the
Okay.
closed is going to be different.
Yes. Because if this is my closed end, and I send my sound down, is it able to leave the closed end?
No.
No, it reflects, actually, and it comes back.
Correct.
So actually, you only get a quarter of a wavelength, and then it has to come back to escape. So in this length of space, you just get a quarter of a wavelength.
Right.
If we follow the same pattern we followed back here, where we said, look, you can go to a half, from a half to a whole, to 3 halves, to 2, the pattern would be 3 quarters, 5 quarters, and so on. And so we end up filling all of the gaps. And this is how our musical notes are generated. You can close a pipe off. This is actually done in music in an instrument called the French horn. So which one is the French horn?
Is that the one with the curls?
Yeah, the pipes tend to go in every possible direction, and then there's sort of this big megaphone thing at the end of it, and the input valve is there. And what happens is I've seen the French horn player put their hand inside of this big funnel at the end, all right, and they block it off. Well,
Attempt to muffle the sound.
yeah, and it muffles, and it also forces the sound waves to come back through and leave at a different point. So this increases the possibility of the notes that the French horn can play. And the reason why I like to bring up the French horn is because we also determined that it's the air inside of the tubes that's vibrating. It's not the tubes themselves, right?
Correct.
So how in the world does the sound get through the French horn? Because remember, we just drew this, right? It's all these twists and turns and curls, and then, oh, it just magically leaves. How is that possible?
Well, because they're traveling through there.
Okay.
It's actually compressions.
Wouldn't they get stuck, though?
Going around the turn? No, because you can hear me when I'm outside the door shouting. You can hear me inside the door. It's not like a flashlight where you can't see the flashlight
Ah.
because the waves must go around the corner.
So it's the property of diffraction, of waves, bending of waves around, and that's the key word, around a barrier. They're not going through. They're going around the barrier. So the qualification for diffraction to occur is the wavelength has to be bigger than the opening. Actually, it has to be greater than or equal to the size of the opening. So here, the sound waves have a bigger wavelength than the opening of the French horn. So the sound waves will bend
No problem.
and go through. In the case of, you talked about the door. Okay, so if this is the classroom over here, and I got somebody standing out here by these lockers, and they clap, you know, that is going to go out in all directions, and it's going to bend and go around. In the case of my classroom, I can often hear Mr. Schreiner while both of our doors open, and he'll be talking and explaining things to his students, and that those sound waves will leave his door, they'll go out into the hallway, and they'll also bend around my door and enter my classroom. And I'm sure that he experiences the same phenomenon. The sound waves are not going through the wall, though. They're going around the wall. It's a bending around. But we've got to meet this qualification. The wavelength of the wave has to be greater than or equal to the size of the opening.
Right.
Light can't do that because the light waves,
Only travel in a straight line.
yeah, light doesn't diffract through a door. Okay? It doesn't diffract through a instrument. It needs a really tiny opening. It needs a slit, is what we would call it. So light, if you want to see diffraction of light, you have to do something or see something called the double slit experiment. And that's way beyond the scope of this class. I believe that almost covers it. The last thing, of course, we would like to continue to remind you of is this wave equation, where wave speed is equal to wavelength times frequency. Do not forget about this. Remember the units, because if you don't remember the units, the equation is probably meaningless. I think that covers it.
It covers it.
So signing off, this is Mr. White.
And Mr. Sapp.